Hey everyone, welcome back to my Calculus 2 series. In today's lesson, we're going to be talking about improper integrals. So in previous lessons, when we were talking about definite integrals, we were used to seeing a definition of a definite integral that goes along the lines of something like this. We would have the integral and we would have these two bounds, a and b, and basically the integral would be continuous on that entire interval. It would have no infinite discontinuities, and again, everywhere within that interval, the function f of x would be continuous, right? But there are multiple functions where they don't really fit this definition. So there's functions that aren't continuous on certain intervals. Maybe at the endpoints of a and b, they aren't continuous. So how do we deal with them? So the kind of starter definition that I'm going to give you of an improper integral. An improper integral is basically an integral that has infinite discontinuities. And we'll see later on in the lesson what I mean by that. So there are two types of improper integrals that we're going to be talking about in today's lesson. The first one has to deal with infinite intervals. This would mean that we have an interval, something like this, where it either ends on positive infinity or it starts with negative infinity. So again, it's not a definite number, it's just infinity or negative infinity. So let's say that we're given this problem, right? We have this function, 1 over x squared, and let's say that we are asked to find the integral from 1 to some arbitrary value that is going to be passed into our function as a parameter, and we're asked to find the area of that up to t. So how do we go about that? Well, as we could see, no matter what value of t we choose, it will kind of yield us a different value. For example, if we choose t to be 2, well then this area right here, that area would be 1/2. However, if we were to choose t to be 3, well then all of this area combined is going to be 2/3, and then if we choose to be, I don't know, t equals 5, well then we'd have an area of 4/5 in total, right? But what if t were to continue to get larger and larger, right? We can compute these values, but essentially, what happens as x approaches infinity? What happens as we go further and further on this x-axis, right? That's what we're curious about with these improper integrals. So one way we can compute this, and actually this is the way that we're going to be using, is first let's compute this area with an arbitrary t. So how would we go about that? Well, we have this definite integral. What I said is make it indefinite. So just be the integral of 1 over x squared, solve that, and then plug in those bounds. So the integral of 1 over x squared, well, that's simply going to be minus 1 over x, right? And then instead of adding a plus c, we're going to evaluate it at the bounds, which is t and 1. So if we go on to solve this, well, that's going to be minus 1 over t plus 1. So we get this expression for the area where t is going to be a given parameter, but we're interested in as x goes to infinity, meaning this t value goes to infinity as well. So if we were to take the limit as t approaches infinity of this expression of minus 1 over t plus 1, well, we can quickly see that this limit is going to evaluate to 1, meaning that the area under the curve starting from 1 onwards to infinity is slowly going to approach the value of 1, which, again, as we can kind of see, I've kind of demonstrated it in this little diagram over here, that slowly we creep towards the area being 1. So this brings us to the first part of type 1, basically infinite interval improper integrals. And part A of this says that if we have this integral right here and it exists for every value such that t is greater than a, meaning that the lower bound is kind of the lowest value that we're dealing with, and then the value of t is only going to be greater than that value or equal to, then we can say that this integral, this one right here, is equal to the limit as t approaches infinity of that same integral, except now we're going to substitute out that infinity and just put a placeholder t that is also correspondent to that limit variable. As we saw from this example, it's kind of what we did. All we did was we computed this part first, and then we took the limit of that later. So we've already done it sort of over here. Now this holds provided that obviously the limit of that integral does exist. If it doesn't exist, then we'll kind of go over what that means and what it means if the limit does exist. But this holds provided that the limit of that integral exists. Now the second part of this type 1 category is basically the opposite. So first we were talking about sort of the interval from a to infinity. This would be a closed interval. And then now we want to talk about, well, what about this interval from negative infinity to b? Actually, again, this would be a closed interval. So now we want to talk about this interval. And how do we translate that? Well, again, if we have this integral running from some value t, and it exists for every value such that t is less than or equal to b, meaning that b is the largest value on that interval and t is less than or equal to that value of b. In that case, this integral right here from minus infinity to b is going to equal to the same exact thing as we did on part A over here, except now the parameter t is just going to go on the bottom. So we're essentially getting as close as we can to negative infinity. So this brings us to convergence and divergence. I said we'd talk about it later, but essentially the improper integrals are called convergent if their corresponding limit exists, meaning if this limit right here exists, then that integral is considered convergent, and they're called divergent otherwise. So lastly, for part C of type 1, if both the integral from a to infinity and from negative infinity to this should be an a are convergent, then we can define the area under the curve f of x from negative infinity to infinity, meaning kind of the whole domain. We can define that as two separate integrals. Basically, we're going to split it up from negative infinity to a, and then from a to infinity of f of x. So here's a quick example. Let's say we were given this problem to compute the integral of 1 over x dx from 1 to infinity. How do we go about this? Well, again, we know that it's just equivalent to the limit as t approaches infinity, and then wherever infinity was, we want to throw in the variable t there, keep the other bound, and then 1 over x dx. We want to solve for this integral as if it was indefinite and then kind of plug in the bounds. So we're going to keep this limit, and then we want to say that the integral of 1 over x, well, that's just equal to the ln of x evaluated at t and 1. So I've done some simplifications and we've gone down to this step right here, and essentially we can see that this limit is equal to infinity, meaning that it does not exist, therefore that integral is divergent. So we saw that the integral from 1 to infinity of 1 over x squared dx, this one exists, it's actually equal to 1. However, the integral from 1 to infinity of 1 over x dx, this does not exist. And in general, this integral right here, so from 1 to infinity of 1 over x to the power of p, is convergent if p is greater than 1, and then it's divergent if p is less than or equal to 1. So before we were talking about integrals that would approach infinity, basically like as the x got very large, we would approach infinity, or we would approach like some horizontal asymptote. But in this case, we want to talk about when x approaches a certain value, then the integrand itself, like the function itself, approaches infinity or negative infinity. So part A of discontinuous integrands or type 2 improper integrals says that if f is continuous on some domain, but it excludes b over here, and it is discontinuous at b, as we saw, then this integral right here from a to b of f of x, well, that's equal to the limit as t approaches b from the left of that same integral, and now we plug in this placeholder of t or whatever variable we decide to use over here. The reason we take b from the left is because b is supposed to be our upper bound, meaning that if we have some sort of function, we could, if this is b, it's our upper bound, we can only approach it from this side. We can't approach it from here because we're asked to find the area from a lower bound a to b, meaning we're on this interval here and we have nothing to do with this part of the graph. And likewise, if we were to have the opposite where now a is discontinuous, then this integral here basically starting from that discontinuous value onto b, which the function is continuous on that value. Basically, we just evaluate the limit of the function, and then we plug the placeholder into that. As you can see, we basically set this limit of t approaching that discontinuous value, and then wherever that discontinuous value is, we just sub it out for t or whatever variable you decided to use in your limit. And like usual with both these integrals, if the limit exists, then it's also called convergent, and if it doesn't exist, then it's called divergent. I mean, the definition is pretty universal for these integrals. And so for part C, basically if we have this function and it's discontinuous on a value that is in between the endpoints of A and B, and then the other condition is that both from that discontinuity to one endpoint of the interval, and from the discontinuity to the other point of the interval, if both those integrals are convergent, then we can say that the entire integral can be split up into the first integral, basically from the start point of the interval to the discontinuity, and then from the discontinuity back to the end of that interval. So let's say we were given this problem and we were asked to compute the integral from 2 to 5 of this function 1 over the square root of x minus 2. One of the things we can quickly notice is that x equals 2 is a vertical asymptote, because the square root of 2 minus 2 is equal to the root of 0, and that would be a vertical asymptote because the denominator would end up equaling to 0. So quickly we can notice that 2 is a discontinuity, and again, the way we can deal with them is by taking the limit and basically subbing out that discontinuity for the value that we use in the limit. So if we were to take the limit as t approaches 2, and now 2 would have to be approached from the right side because it is the end interval. So if we think about some random function like this, right? Let's say this is where 2 is and then 5 is over here, right? Because we're asked to find this area, we can only approach 2 from the right side, because we're not even talking about the left side. We're not talking about the area from -1 to 2. So this interval is kind of like inexistent. We're only talking on the interval 2 to 5, therefore we can only approach 2 from the right side. And now we want to take this limit of that same integral, except now we want to sub out the discontinuity for the value of t, and then the upper bound is going to stay the same. Now we can go on to do a simple evaluation. Now that we've broken down this integral as far as we could and evaluated it, all that's left to do is take the limit, and we can clearly see that the limit is going to equal to 2 square root 3. Therefore, this integral is convergent. So the last section that we're going to talk about is comparison tests for improper integrals. And basically for this, we want to compare two improper integrals. So for this case, let's suppose that we have a function f and g, and they're continuous functions, and f of g is going to be greater than g, f of x is going to be greater than g of x, but they're both going to be greater than 0 on some sort of interval. And I've kind of drawn a little representation of them, of what they might look like over here. And so for that, we have these two properties that we're going to have about comparing f and g, and especially their integrals. So the first property is that if the integral of f of x dx is convergent, meaning this larger one up here, then definitely the smaller integral is also convergent. We can think of it as like this larger integral, the one that's higher up, if that's convergent, then all of the smaller ones making it up must also be convergent. And we can kind of apply the same logic to part B. So that means if g of x, if the integral from a to infinity of g of x is divergent, then the integral from a to infinity of f of x is divergent, meaning if the smaller integral is divergent, then the larger integral can't be convergent. It must be divergent, because the larger integral is kind of made up of these smaller ones. So f of x is sort of made up of g of x, kind of like in a sense. So if g of x is already divergent, then there's no way that f of x can be convergent. So it must be divergent. So yeah, that's it for today's lesson on improper integrals. I hope you enjoyed the lesson. If it's helped you out at all, please like and comment as to what I helped you out with. Like usual, if you're new to the channel, please like, comment, and subscribe, and I will catch you guys in another video.